Alright, and here is, well, we're going to start with RC time constant circuits, but time constants in general, we're going to go ahead and talk about them for just a minute. So time constants looks at the amount of time that it takes for those reactive components to be fully functioning. If you remember your ICE and your ELI, some of those parts, like for instance ELI, where current lags, and ICE, for this example, where voltage lags. So you don't immediately have the entirety of those components when power is applied. There's a certain amount of time that it takes for those reactive components to become fully functioning. So that's essentially what time constant circuits look at. They look at the amount of time that it takes for the component to be fully functioning and what, in this case for a capacitor, what level of voltage is on the capacitor at those various times. So they break it down into a formula that helps you to figure out those time constants. And we're just going to kind of run through some of this and we'll discuss it as we go. Okay. So for this, what is time constant 1? So we figure that out by taking R times C. In this case, that would be 300 times 2 micro, and we get a value of 0.2 milliseconds. So the amount of time for one time constant is 0.6 milliseconds. All right. So then here's another sample question. How long will it take the capacitor to fully charge? Well, that's a loaded question, actually. But we typically, and I'm going to show you a graph here that we use for time constants. So typically, we use 5. Engineers will go further out often because you'll notice 5 is only 99%. What's happening here is you gain or lose 63% at each time constant. So at the first time constant, if you are charging, say, you would have 63% of total voltage. At your second time constant, you would have that original 63% plus an additional 63% of what remains, which gives you that 86% that you see at time constant 2. And then the same for time constant 3. You have the original 86% plus 63% of the remaining amount added to it. And that's how you get those, each additional percentage, is that they've taken the original percentage and then taken 63% of what remains and added it to the original percentage. All right, so as you can see, you get out to time constant 5 and you hit 99%. Now, clearly, if you are constantly taking 63% of that remaining value, you're not going to reach 100. You can come really close to it, but that's why we mark it off at 5. We're saying, okay, 5 is close as we're going to get because we're not going to go way out into percentages, which is what they would do probably in engineering. And the same idea is happening on the downward swing. You'll see there's an upward swing line. So right here, this line goes up. That's your charging for your RC, or your energizing for your RL circuit. And then you've got this line here that goes down, and that is your discharging for your RC circuits or your de-energizing for your RL circuits. And it works the same way. You just start at 36% and then you take 63% of the remaining amount, subtract it from the original, and you get the next one, which is 14% if you round it up. Okay, so now that we kind of understand how the graph works, we can really look at doing the next question, because it wants to know how long does it take the capacitor to fully charge. Well, if we are going to say that it is fully charged at 5 time constants, then of course it would take whatever time it is for one time constant and multiplied by 5. Okay, and so that's what we do. We take 0.6 milli, which was time constant 1, and we multiply that by 5, and we get 3 milliseconds. So that is how long it takes the capacitor to fully charge. All right, now here's where we're really going to start using our graph. What is the level of charge on the capacitor at time constant 2? Okay, so we're looking for an amount of voltage. We're going to look here at time constant 2. You can see the 2. Here's the time and time constants. So there is 2, and we see we are at 86% on time constant 2. So what we would do then is take 60, which is the total voltage on the circuit, multiplied by 86%. Now, if you're putting that into your calculator, it would just be 60 times 0.86, and you would get 51.6 volts. So, at time constant 2, which is 1.2 milliseconds, right? Because we would take 0.6 milli times 2, 1.2 milliseconds is 51.6 volts on the capacitor. So you see it doesn't have its full voltage yet. It's only got 86% of total voltage at time constant 2. So that's what I meant when I said we're looking at the amount of voltage on our capacitor at a certain amount of time until it becomes fully functioning. Now, when it gets to time constant 5, we're considering it to be fully functioning. So essentially then you would expect to see nearly 60 volts on it. It's going to be 99% of it. So it'll be just less than 60. But for all intents and purposes, it's going to be 60. And remember, all of this is happening in very small fractions of time. I mean, this is 1.2 milliseconds. So it's a fraction of a second. All right. Now we're going to look at a little bit more complicated RC time constant circuit in our next video.